Welcome to the third episode of How Do Rocket Engines Work. Previously, we learned about open cycle engines and engines that didn't use fuel for their gas generators or preburners. In this video, we are gonna talk about fuel rich and oxygen rich closed cycle engines. The closed cycle or the staged combustion cycle. Something rocket engineers quickly tried to master after seeing the potential for the incredibly high performance in the closed cycle. They don't just attach the gas generator exhaust pipe to the main combustion chamber and cross their fingers. That would be very bad for a few reasons. The pressure through the turbine is usually kept at a minimum, and we lose most of them to spin the turbines. So, the main combustion chamber gas would want to go backwards through the system, and of course, that's not good. But also, if you are using RP1 or any other carbon based fuel, that sooty exhaust is terrible for injectors because you would likely clog your engine up and they would cease to function. First off, just using a little fuel and oxidizer to run the gas generator, we actually put all of our fuel or oxidizer through the gas generator and the turbine. And now we won't call it a gas generator. It will actually be considered as a pre-burner because it's exactly what it will be doing. Burning the propellant just a little bit, pre-burning it before it gets into the main combustion chamber for the real burn. Now remember, again we want to flow either all of our fuel or all of our oxidizer through the pre-burner and the turbine, and depending on which one it is, that type of closed cycle it is. So either fuel rich or oxidizer rich. Let's start off with the oxidizer rich closed cycle. Since it was the first closed cycle rocket engine ever developed, the Soviet engineers were able to overcome the challenges of the oxidizer-rich staged combustion cycle in the late 1950s and already built the S-1 5400. The Soviets chose to go with the oxygen-rich staged combustion cycle because when running on kerosene-based RG1 or RP1, you would run into the choking and sooting issues. So this means they decided to run on all of their oxidizer through the turbine and then pipe that into the main combustion chamber and pump just exactly as much fuel as they need to make enough heat and energy to spin the pumps fast enough to react to make the high enough pressure and heat, because remember, it will drop as it runs through the turbines as it is converted into mechanical work, and it will go into the combustion chamber. And what's our rule? Remember, always pressure flows from high to low, so the pressure inside the pre-burner needs to be much higher than the pressure inside the combustion chamber. That way, when the pressure drops across the turbine and then drops again in the injector, it is still coming into the main combustion chamber with some margin of safety. A good rule of thumb is to get 2 times higher pressure from the pre-burner through the turbine and about 20% higher pressure between the back of the injector and the combustion chamber. But the engineers tended to avoid these as they gain confidence with an engine and then try to pursue higher and higher performance. All of the oxidizer will get compressed up to very high pressure since it will flow through the turbine, but that same thing isn't true for the fuel. The majority of the fuel will just flow into the combustion chamber, so it only needs to be pressured as about that 20% higher pressure than the combustion chamber, but we still need some of the fuel to be high enough pressure to power the preburner. So in this case there's actually stages to the pump. Most of the fuel will go through the first stage, which gives it to be high enough pressure for the main combustion chamber, but then some of it will go into another stage of the pump that increases the pressure to be high enough pressure for the pre-burner of the oxygen rich stage combustion cycle. The oxidizer rich staged combustion cycle is very hard since you are creating high pressure hot gaseous oxygen which CO loves to react with absolutely everything. It requires fancy metal alloys that can handle those extreme environments. The Soviets mastered this as the majority of their engines were oxygen-rich staged combustion cycle, including the NK-15 and the NK-33 for their N1 and the RD-171 for their Energia rocket. They also built the RD-180 on the Atlas V. The US recently flew their first ever oxygen-rich closed-cycle engine, the BE-4, on board their Vulcan Center rocket.
And liftoff of the first United Launch Alliance Vulcan rocket, launching a new era in spaceflight to the moon and beyond.
The United States didn't completely give up on the staged combustion cycle. They just went the other way around. They pursued fuel-rich staged combustion cycle for an engine at the heart of an icon, the RS-25 on the mighty space shuttle. American engineers thought, what if we basically swap the process of the oxidizer-rich staged combustion cycle and just put all of the fuel through the turbine and just use a little bit of oxidizer, kind of like the most gas generators. When that avoided the issue of having hot gaseous oxygen, that brings up another problem of choking and soot. But wait, what if we didn't use RP1 or any other carbon based fuel in the first place? When the engineers were designing the main propulsion system for the space shuttle, they went with the liquid hydrogen and liquid oxygen because they can run hydrogen fuel rich through the preburner and not have it create soot, and the engine will happily run. With hot gaseous hydrogen, this seems like a pretty obvious solution, but wait, fuel-rich staged combustion cycle comes with its own challenges besides the potential for such, especially if you are using hydrogen. Hydrogen is extremely lightweight, which of course means it takes up a lot of space and tanks, but it also takes a large preburner with lots of stages to get up to the right pressures. It's common and perhaps the most simple to have a single shaft for your preburner and your turbine, assuming everything on that shaft can operate at similar speeds. And although single shaft hydrolox fuel rich closed cycle engines have been made, like the Soviet Union's the RD-0120 at the heart of their Energia booster, the US went with a different solution that raised its own set of problems. Their design for the RS-25 called for dual preburner on the two different shafts, both fuel rich. One preburner pump would power the fuel pumps and the other would power the oxygen pumps. So, looking at our diagram here, you can see that two separate turbines and preburners have a dual shaft fuel rich closed cycle engine. Of course, one preburner powers the oxidizer and the other powers the fuel pumps. Since these preburners run fuel rich, it means all of the fuel will go through one of the preburners and turbines before it goes to the main combustion chamber. So we see that approximately half of the fuel flows through each preburner and turbine, and exactly opposite of the oxidizer rich closed cycle engine. In this case, only a little bit of oxidizer goes into the preburner, just enough to create high enough energy to spin the pumps up to the right speeds to create the high pressure needed to get the propellant through the preburner and turbine and into the combustion chamber, and again opposite to the oxidizer rich closed cycle engine. In this case, most of the oxidizer will only go through a single stage pump that gets it to be high enough pressure to go into the main combustion chamber, but the bit of oxidizer that goes into the preburners will flow through the second stage of pumps to get it up to those high pressures So the RS-25 was the United States' first closed cycle engine, but it wasn't the only fuel-rich closed cycle engine developed. The Soviets also made the RD-56 and the RD-57, which were both fuel-rich closed cycle combustion hydrolox engine, developed for an upgraded N1 variant that they didn't make. So the fuel-rich stage combustion cycle adds one bit of complexity for the other. But even so, there is still one cycle type that combines many of the pros and cons of both cycles to form one ultimate and confusing engine. But that's a story for another day. If you have enjoyed watching this and have gained some knowledge, you can subscribe to our channel, and if you want to support me financially, you can join my Patreon. Thank you. Goodbye.